announcements are in order here. Number one, attendance in this class is mandatory. There's no point that 3/5 of the class doesn't show up. So I'm going to reiterate and re-emphasize that attendance in this class is mandatory. And there's no excuse beyond that. Number two, please look up and go through the reading material that's already been uploaded on the website. 3, attend the tutorials. Not many people are coming up to the tutorials. We have 7 or 8 sessions lined up for the tutorials at differing times. So I'm sure that one of these times is going to overlap with your free time. So do show up in the tutorials. Number 4, I have my office hours as well. Please feel free to drop by. And the 5th or the 6th announcement is that quiz number 3 is going to take place on the 12th of April. Thursday, the 12th of April. Alright, so what I'm going to try to do today is I'm going to build up towards the hydrogen atom. So far we've been looking at one-dimensional quantum mechanical problems. And now I would like to, Mehan, could you turn off the projector so that students don't pay attention to the projector for time? So I would like to talk first of all about two-dimensional wells. Suppose instead of having a one-dimensional well, an infinite well, I instead have a quantum carpet. In which I have the following configuration. I have a square in flat land in a two-dimensional world, and a particle lives inside this flat land. It's two-dimensional and it's square, which means that each length is L. So I define an x-axis. This is my x-axis and this is my y-axis, which is perpendicular to the plane of the black hole. Inside this carpet, it's two-dimensional, the potential energy of a particle is 0. And outside, it has impenetrable walls. On the edges of this carpet, there are impenetrable walls. So the potential energy goes to infinity at the walls. Okay? So this potential energy is approaching infinity. It's a hard brick wall. Likewise, here the potential energy goes to infinity. This is an example of a two-dimensional well. You can imagine that the particle is trapped inside a two-dimensional cage. It cannot go outside of the cage. It cannot tunnel through. It cannot leak through because the potential energy is actually going to infinity. So this is my picture here. And the particle is now destined or doomed to exist within the carpet only. It cannot penetrate outside. Now we would like to solve the Schrodinger equation for this two-dimensional problem. So the goal is to actually build up steam for studying the hydrogen atom and atoms and how is the periodic table built up. So I stepped out of the one-dimensional world, which is very artificial, though realizable. I've now moved on to two dimensions. So the Schrodinger equation in two dimensions is exactly identical to the one-dimensional Schrodinger equation. The only difference is that I now have to account for 3 variables. And those variables are x, y, and the third one is, of course, our favorite loyal time. It always sticks to us. So now we have the Schrodinger equation, which is given by minus h bar square over 2m partial square and partial x square. Now our wave function is now a function of 3 variables instead of 2. It depends upon x, it depends upon y, and it depends upon time. So far so good. If I just had x, I would have a one-dimensional problem. But now I have introduced this second variable as well, y. Therefore, I will have to have a derivative, a second order derivative with respect to y as well, in addition to the second order derivative with respect to x. So I added an additional term. Okay, so I'm short of space, so I'm going to extend this equation as a multi-line equation. I'm going to the next line here, plus the potential energy, which is now a function of x and y, not just x. Psi x y t. This must equal iota h bar, the time derivative of the wave function. So all of this is the two-dimensional Schrodinger equation. If I ignore this y, if I slash out this term, then I'm left with nothing but the one-dimensional equation. So the two-dimensional equation is different because I have the introduction of an additional term, which is this term over here. Now I would like to find out my wave functions. So conventionally, as is always done, I would like to use the technique of separation of variables, which means that I break up my wave function into a spatial part and a temporal part. That's what I did with this one-dimensional equation as well, which means that I now have a function that only depends upon x, I call it small psi, and a function, let's call it phi, that only depends upon y, the second variable, and a function f that only depends upon time. Alright, so I break up my wave function, the spatial temporal wave function, into its components, into the factors. Now I plug in this factorization into my equation. That's what I do. The technique is very similar, nothing special about it. Look, the mathematics looks daunting. Strange symbols, partial derivatives, an iota sign. But if you come to think of it, once the initial fear is over, this is something that is easy to understand. So what I would like to do now, I just reproduce these terms, minus h bar squared 2m, and I take the partial derivative of this object, the second order derivative with respect to only x, keeping y and time constant. So I take partial square partial x square. Now out of these functions, only this function depends upon x. So this is psi, and these terms just come along for the ride as far as this term is concerned. So I put phi here and f here. Since these terms don't depend upon x, they just come for the ride. Okay? There's no need to differentiate these because these are constants as far as x is concerned. Plus, the second term is minus h bar square 2m. Now psi and f come in for the right, and I have partial square partial y square of phi, which is a function of y. This is the second term over here. Plus, now inside the well, the potential energy is 0. Outside the well, the wave function is 0 because the particle can't go outside the well. So I am solving the Schrodinger equation in the limits that if this length is L, this length is L, which means X is L here and Y is 0. So this point is actually L comma 0. This point is L comma L. This point is 0 comma 0. Whereas this point over here at the back is 0 comma L. Okay, the first number in the order pair represents the X coordinate, whereas the second number represents the Y coordinate. Alright, now inside the web, which means that I'm dealing with X smaller than L, greater than 0, and at the same time Y is between 0 and L. So I'm inside the web. I'm on the carpet. Alright. Now I look at this term here. Inside the well, this term is 0. Okay? So this completes the left hand side. Yes. Alright. So the right hand side is partial iota h bar. Now if I take the time derivative of this, only this is time dependent. So I can write partial f over partial t. And these factors come in just for the right, psi and phi. So this is my Schrodinger equation. Yes. Where? Okay. Now this is the Schrodinger equation. I divide both sides by the wave functions. So what I would like to do now is minus h bar square 2m partial square psi x partial x squared. Now I divide this by the entire wave function, which means I divide by psi phi f. I'm left with 1 over psi. Now I take the second term. Okay. Now I take the third term. On the right hand side, the first term. This gives me now notice this equation here. I have three terms inside the equation. The first term only depends upon x. And it's a variable of x. It changes with x. I change x, this term is bound to change. This term can change. It has the potential to change. It's a function only of x. So I have only x here. And I only have y in this term. And I only have time in this term. Now I have these only factors, and each one of them has the potential to change. If I change x, this might change. But if this changed upon changing x, none of these terms are going to change, because a change in x doesn't affect this term, and a change in x doesn't affect this term. So this term shouldn't change with x as well. Even though it appears to be a function of x, it is actually independent of x. Alright? So I have three terms here. This depends only on x. Now I can change x in my problem. I can go from one position to another position. I can change my x, no doubt. So I would like to find out how the wave functions change. So if I changed x, only this term has the potential to change. Because none of these terms depends upon x, this term cannot ever change if x changes. This term cannot change if x changes, and I keep everything else constant. This means that this term should also be a constant. Otherwise, you cannot satisfy this equality. So this function of x is actually equal to a constant. it doesn't change with x as well. Each one of these three terms is equal to some constant. Let's call this constant E. Let's call this constant E1. Let's call this constant E2. Now I have the relationship. I'm calling these constants E's just because I know actually that these are going to turn out to be energies, but you don't need to know this beforehand. The symbol E is just a symbol. So I have the relationship that E1 plus E2 must equal E. Now E1 equals this term, E2 equals this term, and this term equals E. I have three equations. Starting from one equation, one partial differential equation, I pop out three independent equations. One of these equations is that this equals E. And if I solve this equation once again, I would get Fe equals e raised to power minus I e t over h bar. This is the time dependent part of the wave function. So you can solve this equation. We've already done this for the one-dimensional example. If I were to solve this equation, I get this solution. Now this f actually comes in here. My goal is to find the entire wave function, so I've determined f already. Now one equation is simply minus h bar squared 2m partial square psi x partial x squared 1 over psi x equals E1. Now I can manipulate this equation, and since I only have x's here, this entire term seems to be a function of x, but really it isn't. It just is independent of x, as we just argued. So since the variation is only with respect to x, I can put a normal derivative here as well. D squared, dx squared. It doesn't make any difference. So if I were to do some manipulations now, I can write d squared psi over dx squared equals minus 2m over h bar squared E1 psi x. Okay, so I just done some juggling with the coefficients. I moved one coefficient from one side to the other side. Now I can take this term to the other side of the equation. Plus 2m E1 or h bar squared psi x equals 0. Now does this look familiar? It's just the one-dimensional Schrodinger equation in the x-axis. Okay? So if I were to solve this equation, once again, I could write down the auxiliary equation as s squared plus 2m E1 h bar squared equals 0, which means s equals plus minus iota 2m E1 under root divided by h bar. Okay, so I write down the auxiliary equation, I take this to the other side, I find out the square root of both sides, this is what I get. So my solution for the x component of the wave function turns out to be some coefficient a plus multiplied by exponent of one of the roots I. Now let's call all of this k1. It has dimensions of k1. You've already come across terms of this kind, square root 2me over h bar. This has dimension of the wave number. Okay? Just the one-dimensional equation. So we've actually extracted two one-dimensional equations from a two-dimensional Schrodinger equation. One of these equations is psi x equals a I k1x plus b e minus I k1x, where k1 is this term here. Now I need to find out these coefficients. I know that at the boundaries of the wall, whenever x equals 0, my wave function actually must go to 0, because the wave function has to be smooth. Outside the wall, the wave function is already 0, so it must be 0 at the edges as well. So if I put x equals 0 here, this becomes 1, this becomes 1, this is 0, a plus b equals 0, which means b equals minus a, so I'm left with a ei k1x minus e minus I k1x. Now this is 2 iota a sine of k1x. So I have found out the x component. I have now determined exclusively the x component of the wave function. I've already determined the time component. Yes. Which one? This one or this one? This one? At x equals 0, the wave function must be 0. Why? Why should it be 0? It's continuous, because outside in this region the wave function is 0, because the particle cannot exist in the impenetrable region. This is classically forbidden, and it's also quantumly forbidden, because the potential energy is infinity. It's a hard brick wall. So if the wave function is 0 everywhere here, it must also be 0 at the edges, because the wave function changes smoothly. It always changes smoothly. Therefore, at x equals 0, which means along this boundary, all along this edge, x is 0. Along this edge, the wave function has to be 0. So this is 0, and I just put 0 here, I get 1. So a plus b equals 0, which means b equals minus a. So this is how I arrive at this term. This is exactly similar to the wave function we derived for a one-dimensional problem. But the additional icing on the top here is that this k1 is quantized. This k1 cannot take up arbitrary values. Since we have confinement in the x-axis, we already expect some kind of quantization to exist along the x-axis, which means that k1 is quantized. If k1 is quantized, then this E1 must also be quantized. Okay? Now, how do I know that this is an energy here? Because I know that this is my solution. K1 must have dimensions of 1 over meters, because 1 over meters times meter gives me a dimensionless phase. This has to be a phase. So this is 1 over meters. So if all of this is 1 over meters, I can find the dimensions of this object here, E1, because I knew the dimensions of m and h bar. This is joule second, this is kilogram. And all of this is 1 over meters. So this has to be joules. Okay? So E1 has dimensions of energy. Now if I were to find out the quantization condition, I need some additional constraint. So what kind of constraint can I use to find out the quantization of K1? What's the value of K1? How do I propose that K1 is quantized? Can you come up with an idea, please? Someone at the back, please. So I'm proposing that K1 is quantized. Now how do I know that? So you can't just believe me, you can't just trust me, take everything that I say for granted. You'll have to convince yourself that this K1 is quantized. Now how do I do this convincing process? Yes? Now the derivative need not be continuous because we have an infinite wall. So for an infinite potential energy, the derivative can be discontinuous. That's what we saw in the infinite well as well. The derivative can be discontinuous if the potential energy is infinite. So that's not the condition that we like to use. There's another condition, yes? The integral. But the integral will actually just give the value of a. That's the normalization condition. I would like to put some constraints on k1. Yes? At L. Very good. So, there's nothing special about this edge. This edge equally deserves our attention. So at this edge, which means when x equals L, the wave function has to be 0. Because outside this edge, the wave function is 0. So the constraint that I have is that if I were to put x equals L here, then this wave function must be 0. So how do I do that? So the other constraint is that psi at x equals L must also be equal to 0, which means 2 iota a sine of k1 L must be 0. But a cannot be 0. If a were 0, then I just had a 0 wave function, a trivial wave function, and the particle doesn't exist at all. I need to have some wave function, which means that this a cannot be 0. The only option that I'm left with is keeping this term 0. And this term will be 0 when k1L has precise values. And the precise values of k1L are n pi, which means pi, 2 pi, 3 pi, 4 pi, and so on. Or n is a positive integer. So I have constrained the value of k1. Now my k1 is quantized as n pi over L, which means that my wave function component along the x-axis is just 2ia sine of, now let's call this n1, because I'm using k1, n1, so let's call it n1. 2ia sine of n1 pi x over L. This is the x component of the wave function. Likewise, I can find out what's going to happen to this term. Exactly the same procedure. Exactly the same procedure. Only that now I have some E2 here, some constant E2. And I get phi as a function of y is simply 2i a sine of n2 pi y over L. So now what I've done is that I have constructed, once again, n2 is a positive integer. So what I've done once again is now I have constructed the entire string of functions inside the wave function, because I now have all three. I have psi, I have phi, and I have f. And it turns out that these k's along the x-axis, which I've called k1, and the k along the y-axis, which I've called k2, both of them are quantized. And their quantization is determined by these numbers n1 and n2. So first of all, let's write down the complete wave function. This is the complete wave function in its full glory, with the x component, y component, and the time component. So we started off by stripping off the x component, the y component, z component. So we disintegrated this wave function. We separated out the variables. We put them apart. And then we got three equations. We solved each one of them. And then we string together the solutions back together. We integrate, or we combine all the solutions together. So we separate out the variables. That helps us solve the differential equation, and then we put them back together. And when we put them back together, our overall solution is some big constant a. Now I'm writing a for all of these constants. This is a constant, some a, We call it B, C, anything you like. It's one big constant. It could be complex, which allows for the possibility of this iota here. So it could be complex, a complex number, but independent of all variables. A into sine of one number n1, which is an integer, a positive integer, pi x over L. This is the x component. I multiply this with the y component, n2 pi y over L. And now I want the time factor, which is e minus iota e, which is neither e1 neither e2, it's in fact the sum of e1 and e2, which I'll show you is going to be the total energy of the system. T over h bar. This is my solution to the time-dependent Schrodinger equation in 2 dimensions. And I can plot this, but now I need 2D plots for this. And I have a simulation that is going to show what these functions are going to look like. Alright, so now 1 minute of silence to actually decipher all of this. Just digest what I've said here, and then we're going to talk about energies in a minute. पहले सब जरा खामोशी से आधा मिनट और फिर बात। हाँ जी। So I'm just lumping all of these terms together and defining a new constant A. Okay, I'm not concerned about these phase factors. So this A has to be normalized. This A comes out because of normalization condition. I integrate over the entire area of the carpet. I should be able to find out the value of A. It turns out to be 2 over L at the root. For 1D, it's 1 over L under root. For 2D, it's going to be 2 over L under root. Alright, any questions about this? I'm going to tell you the moral of this story. What do I want to achieve out of this story? But you had a question as well. Yes? No, these K's are not the same. K's. Could be any. No, not necessarily. But all of this is going to lump together in some grand constant. This grand constant can be found out by normalization. So how do I find this out? I find this out in the following fashion. I take psi, I take the complex conjugate of psi, multiply this with psi, and then I integrate over x, and I integrate over y, and I take the limits of x from 0 to L, and I take the limits of y from 0 to L. This must equal 1. This is the grand normalization condition for 2 dimensions. So if I were to solve this equation, I'm able to find out what this grand constant is going to be. And this is something you should be able to do. It's not hard, it's easy to do, because all the x variation is inside this term, all the y variation is inside this term. So when you integrate over x, this appears as a constant, and when you integrate over y, this appears as a constant. So this is easy to do. You should actually do it on your own. It's a do-it-yourself problem. Now the question is about the energies. We've noticed that my K1 equals this, and K1 is quantized. So if I just restructure this equation, it turns out that my E1 is h bar square k square over 2m. This is my E1. In 1D, I have energy equal h bar square k square over 2m, which is p square over 2m. E2 equals h bar square k2 square over 2m. And the sum of these terms, which I called E, which must also be equal to an energy. It is an energy because here if you look, Et over h bar is dimensionless. H bar over T is h bar f, which this is units of energy. This must also be energy. So, and this turns out to be the total energy of the system. Now the total energy of the system is just the sum of these terms. H bar squared over 2m k1 squared plus k2 squared. Now k1 is quantized and k2 is also quantized. This is how k1 is quantized. And k2 is correspondingly quantized in this fashion. It's n2 pi over L. So both k1 and k2 are quantized and they are dictated by their respective integers n1 and n2. Which means that the sum of these terms is also going to be quantized. So the total energy of the particle inside this bound system, which has been confined from all the four directions in a 2D carpet, is going to be confined, and the energy turns out to be h bar square 2m L square pi square n1 square plus n2 square. This is the energy of a particle inside a 2D infinite well, and it's quantized. The energy is actually totally determined by two numbers. One of them is n1 and the other is n2. We have a two-dimensional problem, we get two quantum numbers. These n's are called quantum numbers. In a 1D infinite well, we just had n squared here. Just n squared. The energy was n squared pi squared h bar squared over 2ml squared. Now we have n1 squared plus n2 squared. We have two independent modes, one for the x direction, one for the y direction. There is an n in one dimension and an n in the other dimension. We call them n1 and n2, and both of them contribute. The sum of their squares contributes and determines the total energy. So this energy is now dependent upon two quantum numbers. 2D gives us two quantum numbers. 3D would give us three quantum numbers. If we lived in a four-dimensional world, we would get four quantum numbers. So this E is now dependent upon n1 and n2. So I can put a subscript with this E. Instead of just having En, I now have En1, N2. Alright, now the nice thing is that each one of these is an integer. Yes?
Just one question. In case of 2D, you have N1, N2. Would it be the case if it's 3D or 4D, would you have N1, N2, N3, N4?
Yeah, you could call them N1, N2, N3. So if I had a 3D, now this is a quantum carpet. If I have a 3D box in which I trap particles, such as an atom, or a box, a three-dimensional box of this kind, so inside this three-dimensional cube, the potential energy is 0. The particle is now trapped inside this cube, and outside this cube I have the potential energy that goes to infinity. So outside this cube, the potential energy is infinity. And the particle is now trapped within this cube. It's doomed to exist inside this 3D well. Now inside this system, the energy is also going to be quantized. And now I have three quantum numbers, N1. I can call them N1, N2, and N3. And my energy is going to be pi squared, h bar squared, 2mL squared, N1 squared plus N2 squared plus N3 squared. So now I have three quantum numbers, N1, N2, N3. And these three quantum numbers also appear in the wave function. The wave function changes when either of these numbers changes. So it's the quantum numbers that actually define the state of the system. If I were to define a quantum state for the system, written in Ket, I just need to specify the three quantum numbers. What are the values for each of the three quantum numbers in that particular state? So I could just write, say, N1 equals 1, okay, N2 equals 1, and my N3 equals, say, 2. If I specify the values of each one of these three quantum numbers, I've actually defined the state. That's all that I need to know. I need to know the quantum numbers. I have the formulas. I just put in the values of N1 and N2 in here. That determines what E is going to be. E depends upon these n's. I already know the length. So I have the complete description of the wave function, and I have the complete description of the energy of the system. Yes? So if it's a finite potential, some of the wave function is going to leak out to the sides. It's going to have some penetration length into the classically forbidden but quantumly allowed region. Now the nice thing is the following. Let's bring our attention back to the two-dimensional problem and let's look at this relationship over here. Yes? Oh, you're talking about the hydrogen atom and the principal quantum. All three of them are on equal footing. This is a three-dimensional Cartesian box. It's not a spherical problem like a hydrogen atom. So all three of them are on equal footing. You can't call one of them as principal. All three of them are just the principal quantum numbers. Now let me look at the energy manifold. So what I'm going to do now is going to draw the energy spectrum. Based upon the formula over there for the 2D system. The energy spectrum means in an infinite well, the energy spectrum looked like this. So I had some energy E1, the next energy was 4E1, the next energy was 9E1, then I had 16E1. This is the energy spectrum for a one-dimensional infinite well. And these energies are determined by the values of n. So here n equals 1, n equals 2, n equals 3, n equals 4, n equals 5. So the n determines the energy of the system. And of course I can also have superpositions as well. But these are the stationary states. When you solve the Schrodinger equation, these are the stationary states that you get. And I can determine the wave functions as well. In 1D, just for completeness sake, let me write down the wave function. It's 1 over L under root, which is the normalization factor, sine of some n pi x over L. Now I don't need to put in an n1 here or an n2 here, yes. Under root 2 over L. N pi x over L. I don't need to put in n1, n2 here. Alright, so this is the 1D problem. For a harmonic oscillator, on the other hand, though we haven't derived this result, the energy levels are equally spaced. So depending upon the potential landscape, you can have a spectrum of energy. Now let's find out the spectrum of energies corresponding to that quantized energy levels. Now I need to specify N1 and Nt. And here I have energy, N1, N2, and I'm writing this energy as a function of E naught, where my E naught I'm going to define as this term over here. Okay? This is my E naught. I define this to be E naught. Okay, so I don't have to write this over and over again. I just write down my energy in dimensionless units as E over E naught. So my lowest state, which is the ground state, what values of N would it have? 1 for this and 1 for this. And I would get the energy is 2 times E naught, 1 plus 1. So this is the lowest energy, which is also called the ground state for a 2D infinite well. Okay. Now what's the next excited state? The first excited state, which has energy above this system, above this ground state. I can put a 1 here and a 2 here. So I will get 5 times E naught. Okay? But I can have 2 here and 1 here. This is going to give me the same energy. Okay? Now if I were to write the wave function for this is some A sine of pi x over L sine of 2 pi x over L, 2 pi y over L. Okay? The wave function corresponding to these quantum numbers is given by this. Whereas the wave function corresponding to this combination of quantum numbers is given by A sine of 2 pi x over L sine of pi y over L. And I'm ignoring the time dependent factor for the time being. Okay? Because I'm just writing down the spatial part of the wave function. Now, are these wave functions the same? Would they look the same or different? It would actually look totally different. In this wave function, there is one node in the carpet along the x-axis and 2 nodes in the y, 2 lobes in the y direction. Here there are 2 lobes in the x direction and 1 lobe in the y direction. The simulation is actually going to reveal these patterns. But these are totally different wave functions, but both of them have the same energy. Such states are called degenerate states. Now we have an energy which is twofold degenerate. And if I were to draw the spectrum, I could draw the spectrum in this fashion. I have an energy E naught with a factor of 2. This is my ground state. Then I have 2 energy levels. Both of these energy levels are at the same level. They have the same energy. That energy is 5 E naught. So now I have 2 wave functions with the same energy. So this energy has twofold degeneracy, or is doubly degenerate. The next energy level in this ladder has values of 2, 2. The total energy is going to be 8 E naught. But this is non-degenerate. There's only one energy level of this kind. Okay? So beyond this we have 8 E naught. And this is a non-degenerate energy level. It doesn't have a pair with it. Beyond this, we're going to have 3, 1 and 1, 3. Both of them have 10 E naught as their energy, and they are doubly degenerate. In this fashion, I can build the entire energy spectrum, the entire energy manifold. The question that I would like to ask is, if this carpet was not a square, if it were a rectangle, then this length would be different from this length. Will the derivation change? Does it have any bearing on the derivation that we've done? Just answer my question first. Would the derivation change? Would anything change here? The values of L. So, what's going to change is, here we would have L1, the L along the x-axis. Here we're going to have L2. So the energy structure, this energy is now going to change. How is it going to change? The energy for this rectangular well is once again a function of N1 and N2. It's going to be pi squared h bar square 2m n1 square over L1 square plus n2 square over L2 square. That's only what's going to happen. Now the question is, will you get these degenerate states? No. Because now, if this were 2 and this were 1, this will lead to a different energy if this were 1 and this were 2. So now the degeneracy is lifting, which means that these states will now, one of them will be shifted downwards, the other will be shifted upwards. And this lifting of degeneracy is because I've broken the symmetry of the problem. The key result is that symmetry implies degeneracy. And if I break the symmetry, which means I make a square well, a rectangular well, the degeneracy is lifted. It's washed away. Let's take a 10-minute break and then I have something interesting to show you.